András is going to tell us about observing definitional equality.
Okay. Sorry, just I would also like to look at the time. Okay, let's start. So, hello, I'm András, and I would like to talk about observing definitional equality. So let's start with a problem, a unification problem. Let's try to solve this equation. So we have something with a sigma type on the left side and with the same sigma type on the right side. So this is kind of a sigma. So you have a type, and then we have a pair as the second field. So you can, and we also have three meta variables, this alpha, beta, and gamma. So you can see here that we have alpha being applied to true, which kind of means that this alpha meta variable is a function, and then t and some gamma, and then beta true and u true on the right hand side. And then we try to unify this. And so naturally, we do unification by kind of structurally. So we try to unify the first fields. So for the first fields, we get the problem alpha true equals beta true. But that we cannot solve uniquely because it's clearly not solvable. I mean, we only know that these two these two meta variables should be equal when applied to true, but we have no idea what should happen when they are equal to when they are applied to false. So we just postpone this equation. But now the second fields have different types because we haven't established that the first fields have the same types. So what can we do? Well, at least we would like to immediately solve the second field, like comparing the second fields in this problem, because there we do not have any type dependency. So we only have a type dependency in the first field here. So we would still like to make some progress on the second field because we know that there the types are the same. So in general, like this issue of having dependent telescope and type dependencies in unification can get arbitrary complicated. Like we can try to kind of statically compute like what is a dependent argument, what is a non-dependent argument, but of course we can get arbitrarily complicated kind of patterns of dependency and non-dependency at conversion checking time.
Could we assume that T and U are going to have the same type later on? So it's fine to unify them now?
So the issue is that we don't literally know that they have the same type. They could be just a meta variable and some expression, and then what can you do with that? Like if you solve it, then you now have an ill-typed meta variable solution, such that you instantiate, you get random ill-typed terms in your core language. Okay, so what are the existing solutions? So one solution is just make no progress, block the rest of the unification problem. This is quite easy. Another one, so I have been told that this is the rogue solution. I haven't checked the source, but so you can ignore mismatch types and proceed, and now you can get the random ill-type terms, but the final elaboration output gets rechecked. And I think one clear drawback is, but if you do not have anything to type check, to recheck your output with, like in Agda, there is no kernel, you can only implement elaboration in a well-typed way. from the get-go. And of course, there's a clear performance overhead to doing rechecking. In Agda, we use something which is called Agda unification. This might be considered an unnatural technique, but I don't want to talk about it, maybe in the coffee break. I don't know about Lin and Idris. Maybe that's also in the coffee break. And there's something which is called heterogeneous unification by Gundry, McBride, and Lopez, several works on this. And if there's time, I can talk a bit about it later. Okay, let's do it a bit differently. Let's make the postponed equality observational in the sense of observational type theory. Let's see what happens. So we try to solve alpha true equals beta true. We postpone, we extend the meta context with some equation of this type. And now we can try to compare the second fields of the tuple, like the second fields of the sigma pairing. But we also coerce over this postponed equality. So you can see here that there's a coercion and it has a source type, alpha true times bool, and then it has a target type, bit true times bool. And I intentionally do not mention p here in the coercion itself, because it's very irrelevant, and actually here we don't even need to store it, because this is only for the purpose of elaboration and not for the purpose of having it in the core language, or displaying in user interaction in a kind of a checkable way. So we have here an implicit proof of definitional equality, which is hypothetical, like it comes from the meta context, but we don't really mark it. But then the point of this coercion, this observational style coercion, is that it computes on canonical things, it computes on pairs. So now we can push the coercion inside, and we get the coercion in the first field. But we do not get a coercion in the second field, because there is an intermediate coercion, however, that is a reflexive coercion, and we have a computation rule which says that reflexive coercions disappear. And now we can proceed. So the first problem may or may not go through, depends on what t and u actually are. But then the second problem produces a well-typed solution. Okay, so so how does this system work? So the general idea, we start from pre-syntax, elaboration goes into core syntax plus values plus meta variables plus postponed problems, and this is something which I call partial core, because this is a well-behaved type theory, at least it should be, but this is partial in the sense that we have meta variables and some kind of postponed constraints. And then in the very end, we want to produce something which doesn't have any meta variables and any kind of constraints anymore, and that's something which I call total core. And here in the partial core, we use like a stripped down version of this observational type theory by Pujet and Tabareau. It's stripped down because we don't need any kind of user-facing features, because it is not being presented to the users. It's purely for the sake of elaboration. So there's no term language for proof. We don't have any propositions beside equality. And so there's a work-in-progress implementation that's planned to be production strength. It's part of a larger implementation project. And actually, most of the interesting things that I can say is actually about how to do production strength OTT implementation. So let's get to it. And we have some issues in production. So one is reflexive coercion. So I already mentioned this. You have a reflexive coercion, you can compute it. Or at least you have the definitional equality rule, but how to support this definitional equality rule. And in all the prior works, this is not computed during a reduction or evaluation, it is only computed during conversion checking. So when you reduce something, you actually, you don't reduce this, but when you compare two things, then you can actually notice that you have a reflexive coercion on one side. But I'm not really sure about this thing, because if we hang on to coercions for too long, that feels bad for the sizes of the values and the terms that we are working with. And in our case, in the end, every coercion has to be computed away, because otherwise we have unsolved remaining problems. So we have to go into some total core in the end, which does not contain any coercions. So we might as well compute these eagerly. But that requires some modification to the implementation compared to prior works, because already when you are doing evaluation of something, we might depend on conversion checking to detect that some coercion is reflexive, which means that we have to thread some kind of fresh to Brown level through the implementation to be able to do like a mutual conversion and reduction. Okay, another issue, eta short coercions. So in prior works, the coercion works formally very nicely, but it doesn't work in production because for example, like what happens in the prior works, you coerce any term with this kind of function types in the source and the target, and then you compute a lambda. But if you have a very large record and you use the same kind of eta long rule, you have basically coercion eta expands everything all the time, which is not very good. So what we want to do is to only compute on canonical values. So coercion at function type only computes on a lambda. Coercion at record type only computes on a record. And this is much more reasonable. But now we also want to support the syntax-directed eta conversion checking, which means that now the function application computation has to explicitly account for this kind of coarse neutrals. So now the function application becomes slightly more complicated, because if you apply a lambda to something, then you have a computation rule. But if you apply a coerced neutral to something, now you also have a computation rule, and this is required to still support the syntax-directed eta conversion checking. Okay, and then we have pretty much the same thing for pairs, but yeah, so if you coerce a pair, you get a pair. Then we have FST and SND in some kind of postfix form. So we have to explicitly check that when we are projecting a coerced neutral, then it has to compute to a coercion. Okay, issue 3. So how do we actually represent coercion? So on the previous slide I wrote, but I actually didn't mention in speech, that we are using normalization by evaluation for computation purposes. So essentially, like, the whole unification algorithm works on semantic values in the sense of normalization by evaluation. And one very nice thing that we have here is that we can structure the values so that actually implementing this algorithm becomes efficient and also convenient. So for example, we can choose to represent neutrals in a spine form, so that every neutral thing has a head, which is the thing which blocks computation, and then it has a spine, which is a sequence of elimination, like eliminations which are being blocked. And the nice thing about this is that we have immediate access to the reason that something is being blocked. And in the usual MBE-based unification implementation, so the head can be bound variable or it can be a meta variable. And this is very nice because you can look at some neutral, and if you have some solved meta variable in the head, you can just unfold and compute, and you can repeat until you don't have any solved meta variable in the head. And this is some kind of weak head forcing with respect to meta context. So this is a nice way to basically combine NB with meta context and meta variables. But then what happens if you add observational coercions into the mix? And it's not super simple, because we need at least 3 different ways to represent coercions and also remain production strength. So so the first case, so what happens if you have something which is actually canonical and then you coerce it using a completely bogus definitional equality? So the example here is that you have true, so this is like some kind of postfix elimination. So but in the head you have true, which is bool, but then you coerce it to net, which is complete bogus. But then you eliminate it as a natural number. And so we need an explicit representation of this case, because this is basically an error. Like whenever you have an impossible constraint, you can actually get some values like this from it. And so we need to be able to represent and compute with values of this form if we want to report multiple errors to the users. Because if we, like the first time we get an impossible definitional equation, we can just throw an error. But that's not good in production, because in production we want to report multiple errors to users. And so the second thing is that we still have a coercion of a canonical value, but now this is not actually impossible. So now we have some equation between bool and some metavariable expression. And we also need to represent this because we want to do efficient head forcing with these values. So we need to be able to detect that there is a coercion in the head which could be reduced to a canonical value if we had some new metavariable solution. So this is needed for efficiency. And then the third thing is just you have any neutral and then you need to be able to coerce it. But because we have this eta short coercion, the coercion of a neutral is always a neutral. So this is now some kind of postfix notation of a coercion, which is part of a spine.
András?
Yeah.
For your point 2, is this kind of really a flexible head but blocked on alpha?
Yes. Yes, it is. And actually, we also want to remember that alpha is a blocker. Yeah. Okay. And another issue, this is the last one that I know, coercing indexed inductive types. So in usual OTT, we just do forwarding. And the forwarding is that we don't really have indices. We only have parameters. And then we fix up the parameters by using equations inside inductive constructors. So this is a very standard technique. And it can be, in my opinion, it can be made okay from a user experience perspective. Just present some sugar, which is not forwarded, but internally you just forward everything. But it doesn't work here, because equations are definitional, and they are basically in the meta theory, or in some kind of outer layer of this like partial core. And you cannot put them into actual inductive constructors, because actual inductive constructors live in your real core theory, and this is just definitional equality in some kind of meta theory. So it doesn't make any sense to even try to do forwarding. But then what can we do? Well, what about trying to coerce a very simple example of an inductive type, which is the intentional identity? So if you have a raffle which proves some identity, you can actually coerce it from an ID ATT to an ID A prime T prime T prime, but you need these T's to be the same. So you need a TT in the source, and then you need a T prime in the target, because otherwise this equation is simply not well typed. So in order to compute these coercions, we need some kind of nonlinear matching plus some conversion checking just to be able to detect when a coercion can be computed in a well-typed way. Because like here, raffle is only well-typed when you actually have convertible left side and right sides in the type of the term. And this sounds, to be honest, this sounds a bit painful. So can we do something else? Alternative, just don't bother computing. Like this is, like everything here is a bonus. Like everything here is something extra on top of all existing proof assistant unification implementation. Maybe we just don't want to bother. Or alternative, just make the language users forward themselves. So only support parameterized types in your theory, and this computation rule, and just force your users to forward themselves, and then this implementation is simple. Okay, so an interesting potential feature. So what about this computation rule? Like you'd course, okay, so we don't have enough time.
No. I meant the rule is wrong.
Ah, sorry. So the rule is wrong. Okay.
It diverges. Yes. Yeah, what you wrote.
You mean like you morally disagree?
No. I agree with what you wrote.
Sorry, what is wrong then?
Nothing.
Okay. Okay. Okay, so we have this rule, and it's undecidable, because if you basically every coercion becomes one leg of a definitional isomorphism, so that if the meta context implies like this equation, so if the meta context implies this equation, you can just coerce back and forth, and now you have a definitional isomorphism, and which is just the n-type lambda calculus. So this is not decidable, but it is so nice in unification because if you coerce on the left, like you have a coerced meta, you just shuffle the coercion to the right-hand side and you just solve. You can even have a coercion of a bound variable, which like you just apply a meta variable to some expression, which is a coercion of a meta variable. You just invert your coercion, and then you still make a solution. So this is basically like a general way of getting rid of the annoying asymmetry of coercions. And I do not know any other way to get rid of this annoying asymmetry. Like, it doesn't work if you switch over to any kind of heterogeneous equality, because at some point you still have to introduce some transport operation, and that is going to be asymmetric. And the question is it good? I mean, unfortunately, I don't yet have demos, but this is an interesting question. But a thing to note is that we can only loop if the meta context is inconsistent. So we can only loop if your program actually cannot be type checked anyway. And then how hard is it to make the elaborator loop? I think like it would be a fun exercise, because the source language has no coercions. So the language user has to write the terms which generate the unification constraints, which will become inconsistent. And yeah. Okay, just I mentioned heterogeneous unification, so it already exists, and it is basically a restriction of OTT. And the restriction is just that you cannot have coercions anywhere. You can only have, so we have so-called heterogeneous equality constraints, and you can think about it as having a coercion on one side. You can kind of just pick which side. And then we have rules for decomposing this kind of heterogeneous equalities. And it is also possible to put coercions just around bound variables, because when doing these unification, we have to go under binders. So whenever we go under a binder, we allow just the bound variables to be coerced, but not anything else. And this is sufficient to have a reasonable unification algorithm. And one advantage is that now you don't have coercions in your core language, but it's also weaker because it can represent fewer solutions. And if we want to make it efficient, then we have to use both homogeneous and heterogeneous unification, because if we only use heterogeneous unification, essentially now we always have a coercion on one side, and we always have to compute these types to be able to decompose the equations. So it's kind of, we don't want to forget that the types are the same if we know that the types are the same. So that's why you need basically two modes of unification if you want to use this solution. Okay, so more things and further work not mentioned. Like, how does this work together with control definition unfoldings? Also a essential production feature. Like, you don't want to fully unfold every definition all the time, because it's horrible for performance and also for user interaction. There's also implementation of constraints, and the primary further work is just to get this to demo-able and testable state. And that's it.
So how come there is no overlap with the pattern matching machine? I was expecting you to say, oh, but this we do already in the pattern matching, different pattern matching, and so we can reuse the same sort of step.
So there is no, I mean, so the pattern matching unifier, you mean something like in Agda?
Yeah.
It is very different from the general unifier. So it's like in Agda, it's like it lives in a completely different universe. It's like one is called the left-hand side unifier, and the other is a right-hand side unifier. And they are nothing alike. So unfortunately, no.
So regarding this problem of the transitive, like collapsing, the collapsing of transitive coercions, so I guess
kind of regarding the one to last line, so the fact that it only works in consistent meta context. I guess I have kind of two questions. The first one is, if you always block on the first unification failure, could this still happen, or is this really a thing of kind of doing everything in parallel, and then like you might have a problem in later branches if you had something like this before? And the second question is, can you, like, is this a vibe, or like do you have an actual technical argument to say that this is really only, the meta context has to be inconsistent for this to be possible?
So for the second question, I mean, I haven't formally proved it, but I don't think it's a vibe. I think it's a pretty strong reasoning. So, because if your meta context contains, if your meta context is consistent, so it has like an actual, like you can satisfy it with some solutions. That means that every equation actually in a sound like a satisfiable equation in the definitional equational theory. And which means, and if you have a normalizing core theory, you cannot loop if you only have satisfiable definitional equations.
And for the first question?
For the first question, it's a bit more complicated. I haven't thought in detail, like how can we somehow firewall, try to kind of firewall the explosive elements. And I'm not sure it sounds a bit subtle. Like how can, like because we want to use it, but we also don't want to explode. So yeah.
Take a last one.
So, okay, naive question. You don't keep coercion terms, you only have the types. Wouldn't some things be easier if you also had the term and you could sometimes decide that from the coercion term that you want to reduce without looking at the types? And
coercion term? You mean proofs?
Yeah, because you start by adding an assumption. You say, oh, I had an assumption to the context, but I don't track it in the terms. But in the example you had, well, if you had it in the terms, one of them would be referred, and then you could eliminate the coercion away.
Yeah, I mean, so this is one thing which definitely does not work in real OTT, because you are not supposed to ever look at proof terms because they are definitionally irrelevant. But here, like we can try to do some kind of hackings in the implementation. So for example, one optimization is that you just have a set of blocking meta variables, and you just consider it to be some kind of crude approximation of a proof term. Like you do some coercion, and then you just have a set of blocking meta variables. You can kind of think about it as some kind of proof term, and then instead of recomputing the conversion problem when you, for example, want to eliminate reflexive coercions, you can just look at if your blocking problems are still unsolved. Yeah. But this is also kind of complicated, because as you compute coercions, if you want to be precise, you have to update and compute with these sets all the time. And it might not be actually worth to do this. But in certain situations, yes, and actually in certain situations, I do use these sets of blocking things. It's part of this not mentioned. But generally, I do not in every coercion.
Thank you very much.